So we're recording now. Yeah, so Andrew, thank you so much for having this chat with me. I really appreciate it. As you know, there's lots of people, hobbyists, who talk about recycling IPA, and
Hmm.
I've seen like so many crazy things from, you know, designing these like arc reactor core UV things, like systems with like multiple filters, to just like
Yep.
leaving stuff out in the sun. And it just never really made sense to me from like a
Sure.
science perspective. So yeah, I wanted to chat with an expert like yourself to talk about some of these things. I'm sure
Yeah.
you have many thoughts. So
Oh yes. Well, I mean, I will say that I actually really enjoyed your kind of deep dives, if you will, into your process, where you showed you have a solvent recycler, solvent distillation apparatus. That is the professional and correct way to do it. We have similar machines for all of the stuff that we do here. So kudos to you for taking the step and actually being a pro at it.
yeah,
Now, that's not to say that there isn't some merit to some of these crazy arc reactor sort of filtration systems. So happy to dive in.
yeah. I figure that there's so many people saying that it works that
Uh-huh.
there must be, like you said, some merit behind it, right? Like maybe
Sure.
it's not as efficient as like the
Mm-hmm.
conventional distillation method, but there must be
Yeah.
some truth to it, right?
Yeah,
So yeah,
absolutely. So hopefully I can shed some light on what's going on the molecular level, the chemical level, and just have fun.
yeah. Have fun safely.
Yeah, yeah.
Yeah, cool. So I'll run through a couple of questions that hopefully
Some.
will, yeah, shed some more light on this. So I guess the first most like basic question is like, what is in SLA, MSLA, DLP resin? Like, what is it made of?
Sure. Yeah, well, so I will say that most of your SLA resins are fillers. Most of the time, it's upwards of like 40-50%.
Wow.
We call those plasticizers. So, plasticizers are things that kind of give some pseudo mechanical properties or change the overall property of the material that we're working with. Now, these plasticizers can interact with the base resin itself in many different ways. Each resin manufacturer is going to have their own special plasticizer that they're formulating for their specific reasons. But yeah, so I'd say number one ingredient most of the time is usually always either fillers or plasticizers.
Right.
Which is kind of crazy when you think about it. It's like I'm paying how much money for a liter of resin, and most of it's just
Yeah.
you know.
Yeah. Like that's actually really interesting. Like I didn't know what the proportions were, right? So yeah,
Yeah,
to hear that, I'm paying X amount for Formlabs resins and like 50% of it is maybe just this random filler is
yeah.
kind of interesting.
Yeah. Now, I mean, I will again kind of walk that statement back. That filler does perform function in the resin. Like
Right.
without that, the resin might be incredibly brittle. It might be even like imprintable. Like you're not able to do anything with it.
Right.
So there are reasons why it is that high. But yeah, it's one of those things where it's like it's a do nothing molecule.
Right.
So the next big things are, and I'm sure everyone's kind of heard of these monomers. But generally speaking, most of the time, as a chemist, these are going to be dimers, trimers, or oligomers. So these are smaller sections of polymers, or I'm sorry, monomers that aren't quite polymers in that sense. They are polymers because there's multiple monomers, but they're small, pieces. And that leads us into the next piece, which is actually crosslinkers.
Mm.
So crosslinkers are actually fairly ubiquitous in these resins because they provide a lot more strength or durability to the overall resin, or that's what actually provides a lot of the flexible material or just the general material properties.
Okay.
Crosslinkers, we can imagine these as small chains of a polymer, and then we attach functional groups. So basically monomers to the end of each one of these small, like repeating chains of polymer units,
Hmm.
or I'm sorry, monomer units. And we call these cross-linkers because what they can do is they can actually form different links between polymer chains in the completed resin. So
Mm.
when we start polymerization and we start turning these monomers or these oligomers into longer polymer chains, the cross-linkers kind of get in there and they connect multiple polymer chains together. So, imagine basically tangling a bunch of noodles together,
Right.
so tying knots. That's essentially what those do.
Okay.
Um,
And is it like
yeah,
forgive my like
sure.
naivety around like chemistry and
Yeah.
stuff, but do monomers and oligomers bond together just on their own, or do they require cross-linkers to bond together to form these longer polymer
So
chains?
they can. It depends on the type. And it depends on the chemistry. But
Okay.
yes, generally speaking, monomers will eventually form oligomers, and oligomers will eventually form polymers.
Okay.
And you can have combinations of oligomers and polymers. And the reason why, in chemistry we kind of refer to them as monomers and dimers and trimers and oligomers is, well, because everything's so small, and we like to try and use analogies like, think Lego bricks. We
Right.
can take these Lego bricks and we can click them together, so they have a top and a bottom, and everywhere you click, that's like, oh hey, here's a bond that we're forming.
Right.
Now, being that we're kind of used to Legos, we can take a red Lego and a blue Lego and we can connect them together, and we can alternate between red and blue. But in chemistry, we're really bound to physics and statistics. That doesn't, so what that means is we don't know the number of red Legos that are going to get stuck together and then the number of blue Legos that are going to get
Mm.
stuck together. So this is where statistics comes in. And it's like, if we have a very homogeneous mixture, then we might have alternating red and blue. But
Right.
sometimes we're going to get a red, 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 and then a blue, blue, blue. There's just no way around it,
Right.
you
Right.
know?
Yeah. Yeah.
So in general, monomers, we in these SLA resins, they can be mixtures. So we can have oligomers of a different chemistry and monomers of a different chemistry. Now they are compatible, so they're still mostly acrylate based, so they're
Mhm.
still going to connect together. But what's going to happen is it's going to alter our material properties.
Right.
So we might get more flexible, we might get more rigid, we might get higher optical clarity, we might get more opaque. There's a bunch of different things that we can tune for in building out our resins.
Right. Right. Okay, that makes a lot of sense. And also so I'm aware that maybe this is going a bit off topic, but
Sure.
I find this like very interesting. I'm kind of aware that viscosity plays a very large role in mechanical
Hmm.
properties for SLA resins or photopolymers in general,
Sure.
specifically in terms of like impact resistance, which is probably
Yeah.
one of the biggest problems with SLA resins in
Hmm.
general.
Yep.
What contributes to viscosity in these resins?
So,
Are
so
they the
that
cross linkers that,
plasticizer,
oh,
that
the
plasticizer,
plasticizer?
yes, that I mentioned. So that is the largest contributor to the overall viscosity.
Okay.
So it depends on exactly what we're trying to do. Like with MSLA printing, we have a giant platform that's going down and it's touching a surface. Now, we want to make for sure that we can control the thickness of that surface.
Hmm.
But we also have to make sure that that liquid can flow in, because every time we lift and that's cured, we're removing all of that material. So we're creating a vacuum. And so that liquid's eventually got to flow back in, and then we come back down. Now we can cure again.
Hmm.
So, there's some different mechanical properties that need to be tuned for. But also in general, that plasticizer really impacts the ending product.
Right.
So how flexible it is. Like, in many cases, it gets really complicated when we talk about plasticizers, because for I'll be honest, a lot of chemists and chemistry and just in general, the whole industry, we're not quite sure exactly how plasticizers work
Hmm.
inside how all of these molecules interact. We had a theory that basically it was creating free space in between the polymer chains so
Right.
that they can move and slip around. But more recent studies are showing that that doesn't really account for all of the properties that are coming from plasticizers.
Huh.
So in some cases, there's really complex interactions going on between, maybe it's hydrogen bonding, maybe it's, again, that free radical, or I'm sorry, that free space, maybe it's increasing the polymer swelling. There's a lot of different complex interactions. And I'll be honest, we don't really know how a given plasticizer will impact a material. So in a lot of cases, it's a guess and check,
Right.
So we'll add some plasticizer and we'll see if it behaves the way that we think it will.
Right.
And in some cases, if you add a particular plasticizer, it can actually increase the overall, or I'm sorry, decrease the overall viscosity. So we could have a negative plasticizer, if you will.
Oh, interesting.
So
Okay.
yeah, because it actually changes how it interacts.
Right. Yeah, the world of chemistry to me seems so abstract. Like I just cannot comprehend or cannot like understand how one would
Sure.
go from like a blank piece of paper to like this end product, this resin with these mechanical properties. Like that seems like such a very difficult path.
It is a very difficult path. And I mean, to shed some light on it, essentially what we're looking at is molecular dynamics. And we're basically trying to understand the orbitals of certain electrons and the reactivities of certain electrons and structures. And so this also, in many cases, kind of gets into quantum physics. So we have to be able to predict the electronegativity and the reactivity of a particular molecule. I mean, I'm sure probably in high school we all remember the Bohr model of the nucleus of the atom and then the valence electrons.
Right. Yeah.
Like
yeah.
that's great and all, but in many cases it's completely wrong.
Right. Yeah.
It actually does really well for understanding the concept, but when we start getting into 3D molecules, electrons, we don't know exactly where they are. We have a rough idea, but there's different orbitals and there's suborbitals and all sorts of stuff. So, we have to, as chemists, we have to understand where they might end up and how reactive that makes our molecule.
Right.
Now thankfully we're also building on the shoulders of giants. So, we have a lot of basic compounds that, we've identified and understand, and we know these structures, and, we can kind of build off of that. But when building a new molecule or something else entirely, like, yeah, it's a lot of guess and check, and then basically, oh yeah, this method is not going to work. We've got to go all the way back to the drawing board.
Right. So lots of empirical testing. Yeah.
Yes.
Yeah.
So.
That's super interesting. And I guess my last off tangent question is,
Sure.
do you know anything in the research where people are working at finding a solution to what I mentioned earlier, which is like the biggest problem with SLA, which is actually, sorry,
there's a lot.
There's a lot, yeah.
Sure.
But like from my perspective, with the kind of work that I do, the two biggest are impact strength and temperature resistance, right? Like so heat deflection temperature.
Sure.
And as I mentioned previously, like I've heard that in order to boost those, there's this correlation between viscosity and improving those properties. A, is that true? And B, do you know of any research that's like trying to improve those properties whilst still making the resin less viscous and easy enough to like actually like flow and stuff?
Yeah. So, we here at Gloop, we're making adhesives and stuff. In general material science of the FDM style resins and polymers. We don't focus a whole lot on the SLA, but that being said, there's still a lot of crossover. So I will say that I'm probably not as well versed to answer some of those questions there, other than in general, it comes back to that plasticizer piece. So as I mentioned, from my understanding, in most SLA resins, we are using a lot of plasticizers to get certain mechanical properties. Most resins are going to be acrylate based or methyl acrylate. And so that's this, I actually have a molecule here. So that's essentially this little structure right here. This overall molecule, this is a methyl acrylate molecule.
Oh, cool.
And what we have here is essentially a functional group. So a functional group is it's a structure of molecules that can react, and we can do things with it. It's reactive. Um, and so most SLA resins are going to be acrylate based. So they're
Right.
going to have these acrylate groups right here that we can then break bonds and then form new bonds. So from my understanding, in order to increase overall material strength or certain properties, we're going to have to switch away from acrylate based bonding and,
Mm,
kind of look at other chemistries. And those other chemistries, it gets more complicated in the way that they're able to react,
right.
and their overall structures and all sorts of stuff.
Right.
So in general, I believe that there probably is someone out there working on it.
Right.
Because I mean that's going to be a big thing, but I don't know for sure or certain exactly how successful they'll be.
Sure. Yeah. Yeah. No, that makes total sense.
you know,
And just out of curiosity, that model that you're holding,
yeah.
is that so? Is that a combination of monomers and oligomers that
So
have been
this
bonded together?
essentially is a monomer.
Oh,
So
that's
this
one
right
monomer.
here is one monomer.
Okay.
So yes, basically the black balls, those are our carbon. The white, that's our hydrogen atoms, and the red, that's our oxygen atoms. So this
Okay.
is a methyl acrylate monomer.
Got it.
And
Okay.
so we can turn that into a dimer, a trimer, eventually all the way up to an oligomer, and then if we get long enough, a
Right.
polymer.
Okay. Okay. Cool. Yeah.
Yeah,
Thanks for answering that question.
yeah, yeah, yeah.
Sweet. Okay. Yeah. So I think that helps a lot explain, yeah, what is in the resin.
Hmm.
Um, my next question is, I guess at a molecular level, how does isopropyl alcohol clean the like
Sure.
uncured resin? Like, what is it
Yeah.
actually doing?
So in this case, what we'll have is the surface will be coated with, all of the stuff that makes up the resin. So the plasticizers, the monomers, the oligomers, all that fun stuff, right? That we just talked about, pigments, photo initiators. Yeah, we didn't even get into that
Right.
in that last part. But so really what you're doing is you're mechanically removing the uncured or components that aren't basically in situ cured. So like plasticizers, they don't really play a whole lot in the actual formation of some of these polymer chains. They're just kind of there. As I said, they're fillers.
Hmm.
And so, but they get surrounded by these polymer chains and encapsulated, except for on the surface. And so what we're doing is we're washing those off. So we're kind of either mechanically agitating or we're salivating. And so what that means is that we have they're attracted to, essentially, these molecules are attracted to the solvent molecules, and they kind of they diffuse into this solvent, and they pull it away from the surface.
Right.
Now when we're kind of washing these parts, we can just dunk it in IPA or isopropanol, or any other solvents that are compatible with our resin. There are some that are water washable.
Hmm.
So the solvent, if you just put it in there, it's not really going to remove everything because everything's still sticky. Like resin is naturally sticky. That's because all of these molecules, or these monomers, dimers, trimers, they, for one, are very closely contacted, and they need to slip past each other. But two, they're kind of just attracted to each other based off of their electronegativity, all sorts of other fun things that go down into the structure of the molecule.
Right.
So they want to stick together.
Right.
They have the surface tension, all of that fun stuff. So that's where mechanical agitations also needed to kind of break this up and then pull those into solution over time as you're sitting there washing. That's why, and many times, you have an ultrasonic cleaner, or you have some sort of basically bath that's got a jet or a stirrer in it, where you're constantly mixing the liquid. We're trying to diffuse all of these parts into the IPA.
Right.
Hopefully that makes sense.
Yeah. And is there a difference between, so obviously people use IPA to clean
Mm-hmm.
resin because I guess there's like an affinity between IPA and the components that are in the
Yep.
resin.
Mm-hmm.
But if we are just looking at it from like a mechanical agitation perspective, does that also mean that, let's say, if I were to put a freshly printed part in water or just
Mm-hmm.
any liquid that has a very large
Sure.
amount of agitation, it will still remove a lot of the like plasticizers or things that aren't strongly bonded to
Sure.
the part?
Yeah,
Yeah,
and in many cases, yes, you can do that. Like if you were just to have a you know a a flat part that you were going to print, just say it's a flat sheet, you can take mechanically and remove most of that
right,
resin, and you don't have to use IPA in that case,
right,
right? You can just mechanically remove a lot of that before you go to your cure step. The
right,
IPA doesn't chemically change or alter the resin per se. Now, if you leave your parts in IPA for too long, we've seen that the parts can become even more brittle because what will happen is the IPA will slowly diffuse into that part. And what's really happening there is in many cases, as I mentioned, the plasticizers make up a large portion of this part of this printed piece. And so we're replacing or causing those plasticizers to swell, and then they are
uh,
removed, and then
interesting,
so if you leave a part in IPA for a very long period of time, and then you then take it out and let it dry, you'll notice it'll actually shrink.
right,
It will
yeah,
shrink
yeah, yeah,
smaller than
yeah,
what it was before.
yeah.
That's We've removed all of the plasticizers.
Oh, interesting. Yeah, so this is actually very relevant to a recent kind of discovery that I made. I print a lot of elastic flexible resins with our
Okay,
Form Labs machines, things for like heart models and gaskets and stuff
sure.
for companies. And it was always a struggle to get those types of resins dimensionally accurate.
Uh
And
huh.
what I have found out recently is that it's highly linked to like how long you wash it in IPA, as you're saying.
Mm-hmm.
But B, it's also highly correlated to how long you let the part dry afterwards.
Mm-hmm.
So
Yep.
in that case, I don't know if the plasticizer is just absorbing a lot of the IPA and it's holding it in and it's swelling, and you have to
Mm-hmm.
give it lots of time for the IPA to evaporate, and then it kind of shrinks back, like you were saying, but shrinks
Yep.
back to like the nominal dimensions.
Yep.
Yeah, it's kind of an interesting discovery that I had
Yeah.
observed.
So yeah, absolutely. Basically, what's happening is it's absorbing that IPA and it's swelling to some degree. And depending on the level of which how long you've washed it, you might actually over remove some of that plasticizer
Right.
and cause it to shrink smaller than it would need to be.
Huh.
Or in some cases, you don't wash it long enough and you didn't remove enough of that plasticizer. As I mentioned, that plasticizer is sort of encapsulated. Now, as we wash it, we are also kind of removing some of that plasticizer on the subsurface.
Right.
So if we were to zoom really close in, we'll see this amazing network essentially of cross-linked polymers and then surrounding these plasticizers. So as we wash, we are slowly working out that plasticizer in the subsurface. And then we're curing and hardening that resin all around. If, for instance, we don't wash long enough, there might be some of that plasticizer that's just kind of there. Imagine like a pocket of like uncured resin or that ooey gooiness, right? That
Yeah, yeah.
it's kind of similar. Now, in many cases, there's also going to be other pieces. It's not just plasticizer. It could
Right.
be unreacted resin, all sorts of stuff,
Right.
uncured resin. And then when we go through our final curing process, we make for sure that all of that uncross-linked polymers have either fully cross-linked or fully terminated.
Right.
And we'll get into some of that, I'm sure, later.
Yeah, yeah. And I guess that's why, for example, like if your IPA is saturated and you wash your part, it's still
Hmm.
sticky because all the leftover like monomers, oligomers, like
Yeah, you're
plasticizers,
not
they're still
removing it
there,
all.
right? Yeah.
Hmm.
Yeah.
Yeah.
Okay.
Yeah, and that can build up on the surface, and then when you do your final cure, you can actually. I mean, it's probably unlikely that you're going to see it with the human eye, but you will actually have bubbles or whatever. The voxels that you're formed might not be nice and crisp or whatever, depending on how that uh, all of the material left behind.
Right,
So
right. Yeah.
yeah.
So once the plasticizers and like the kind of leftover components of the resin are washed off, Like what
Mhm.
happens to them? Like what are they doing in this solution of
So
IPA?
they're just bouncing around. They're so in many cases we like to think that it's homogenized,
Right.
but probably more realistically there will be stratification that's happening. So, depending on the type of resin and, the exact chemistry makeup, there will be components of that resin that are not really, soluble in IPA. There
Mhm.
will be parts of it that are, but pigments, those sorts of things. Pigments are oftentimes suspended in our resin, and they're just, again, it's a filler.
Right.
It's just there. And so, in a lot of times, pigments won't actually die or they won't die or homogenize or solivate into the IPA. They'll eventually settle out.
Right.
And sometimes you'll also see this weird, kind of sludge form at the bottom. And it doesn't cure, it doesn't do anything. It's just there. That's where we're having some stratification. It's these components aren't really soluble. There might be some components that are soluble in the IPA, but not really.
Right.
Um, so one fun experiment that I remember having to do back in college was we took isocyanate, so like superglue,
Oh,
cyanoacrylates,
okay.
and we mixed it with a solvent. And we mixed and mixed and mixed and mixed and mixed. We used ultrasonic mixers. We tried hand mixing, and then we had to basically put in an initiator to kickstart the polymerization. And what we were always left with was this weird, crazy, cool network of polymerized isocyanate cyanoacrylates, and it looked like a spider's web.
Okay.
So even though we thought it was perfectly homogenized, it wasn't.
I see.
So, in many cases, we think that it's a perfect homogenization, but it's not. There will be, components that are, but other components that aren't. You
Right.
know,
Right. Yeah. Yeah.
you know.
Um, and can like this might sound like a really dumb question, but I think it's I think it's worth like answering. I think the average person kind of understands what soluble or like dissolving means, but like
Mhm.
what does that mean on a molecular level?
So what it really means is that essentially there's an affinity between these two molecules. So in terms of, I think the most basic understanding, like we could take salt or sugar
Hmm.
and we can dissolve that into our water. In salt, what we would have is sodium ions and chloride ions, and they will actually kind of disperse, throughout. Whereas with sugar, again, it's there. It's not like we're breaking down the molecule sugar. What we're doing is we're dispersing it throughout. So imagine essentially our cup of water, and then we just pepper all of the sugar just everywhere. Like
Right.
it's there. The affinity is that there's some hydrogen bonding that's going on between the sugar and the water, kind of holding it in solution. So it just becomes kind of mixed. And
Right.
so that's really what's happening here in solvation is we're just kind of holding it there,
Okay.
in like a suspension, if you will. But it's not really suspension because it's dissolved. We can't just remove it, because it's there.
Yeah. Yeah.
And we're talking about really, really small molecules here.
Right. So correct me if my understanding is wrong, but basically, if something is insoluble or can't be
Hmm.
dissolved by a solvent,
Hmm.
it may be in a single molecule, but it may be in like a pack of molecules that are
Hmm.
kind of settling out. But if
Sure.
something is soluble in a solvent, then the affinity of the solvent will basically break up or kind of like disperse individual molecules of the solute in the
Yeah.
solution. Is that correct?
So yeah, for instance, we have our methyl acrylate here, and we're going to have our solvents. And so what we'll have is we'll have components of this that have electronegativity or hydrogen bond to the other solvent, and they'll just kind of hold it in place. So wherever that solvent goes, so does our molecule. It's just going to kind of float around, and
Right.
that bond is it's not super strong, but it's still strong enough where it's not like it's just going to fall out,
Right.
you know. And you know, these are really, really small molecules.
Right.
You know, whereas as you know, let's say for instance, we have larger and larger, you say dimers, trimers, oligomers, polymers, that might not actually be fully dissolved. It might just be parts of it because we have functional groups. So maybe only part of that molecule is actually soluble. So it's just enough where, you know, yes, it's in there. We can't see it, but if it gets any longer, if it grows any longer, if this polymerization happens, it can start to stratificate, or it can settle down to, you know, a lower level if you leave it over time, you know,
Mm.
and kind of let gravity, because, you know, here everything is moving, everything, you know, on the molecular level is vibrating, it's resonating. And in liquids we have this thing called Brownian motion. It's just random motion, and so molecules will bump into each other. Now again, we've got to remember these are really, really small things. So eventually, over a long period of time, if a molecule is heavier than this other molecule, it will eventually settle out due to gravity,
Right.
you know, and it eventually will work its way down, and then we'll have distinct layers. If we're not touching it, we're not homogenizing that mixture.
Right. And that kind of leads to how, you know, people
Mm-hmm.
anecdotally claim that you can like decant like the part of the
Mm-hmm.
IPA out and it's like fresh and you can reuse it.
Yeah.
Yeah.
Mm-hmm.
Okay.
Yeah, and you know, so I mean, if you kind of want to go into some of this, like that is, I think the heart of the whole issue. It's like, oh well, yes, I'm washing my prints, and then I see all of this stuff come out the bottom, and I just decant, and I can still continue washing, and it still works. And it probably will, because most of the time when you're washing off the surface of your print, there is light leakage between the MSLA, you know, part, or however you're forming your MSLA part, and the uncured SLA resin. So there's a boundary,
Mhm.
and that boundary is going to have a statistical amount of partially cured, fully cured, and, you know, uncured resin. So as we start, you know, moving out further and further away from the part, we're getting more and more uncured resins, more and more, you know, statistically speaking, monomers and, you know, polymer, or I'm sorry, plasticizers that are just there and existing,
Right.
instead of these pre-polymerized oligomers, cross-linkers, whatever they might be, you know, that are closer and closer to the surface.
Mm-hmm.
So when you wash them, those parts are usually what you're washing off, because they are what's more stuck to the surface.
Right.
And you have a small amount of uncured resin, but a lot of it is more partially cured resin that you're
Right.
washing off.
Right.
And so that partially cured resin is naturally going to want to settle out. So,
Yeah. And these are obviously like longer chains of polymers
mm-hmm.
or oligomers or
Yeah.
whatever. And so in that case, like um, let's say that an individual has washed many parts with IPA and they like keep decanting
Mm-hmm.
it, right? And at some point a solvent will be saturated, right?
Yep. Mm-hmm.
So if they continue doing that and they're using fully saturated IPA to quote unquote wash
Mm-hmm.
parts,
Mm-hmm.
is the method of cleaning parts no longer related to like the molecular affinity between IPA and the plasticizer, the monomer, the oligomer, and more
Mm-hmm.
just mechanical agitation at that
Yeah.
point? Okay, and like
Yeah.
statistical like mechanical agitation.
Yeah, yeah.
Right.
So at that point, like if you're taking a fully saturated solvent and you're trying to wash your print, you're just mechanically removing whatever's on that surface.
Right.
Now, that's not to say that there aren't other reactions that are going on inside that solvent. So, for instance, if we're dealing with acrylate-based chemistry, and since I already mentioned everything's just kind of bouncing around already, occasionally if you get two molecules, so two acrylates, hopefully I can pick these up without them falling apart. They're all magnetic.
Oh, okay.
Eventually, we have these functional groups. If you slam the molecules in at just the right angle with just the right amount of energy, you can actually get these to react and polymerize.
Mm,
So, you know, in theory, statistically speaking, there will be some degradation or some polymerization that can happen. It's very, very unlikely.
Right.
But since we're dealing with resins that have photoinitiators, these are things that are radicals, or they generate radicals. And so the most basic radical that we can kind of talk about is a peroxide. So here we have two oxygens and two hydrogens, so hydrogen peroxide. If we were to split this, we now have radicals.
Right.
We have an unbonded, basically face here. So we can form another bond. We have, an odd number of electrons. And so most or all organic molecules will have an even number of electrons. They're stable. Those are stables. Our radicals will have an odd number.
Right.
And so when we polymerize our methyl acrylate here, we will actually take this radical, and it's called propagation or radicalization, and then propagation will attack this double bond right here. And so this double bond will break, and then now we terminate this end of this molecule, and we have a free face, another bond that we can form. So we still have an
Oh,
odd number of electrons.
okay. And that can
And
then bond with like
it
other
can
free
bond with
radicals
another
and
one.
right.
It can either bond with another free radical, so we can take this other free radical and we can bond here, and now we have a termination. So that would be termination, and this would now be stable, and there's no more functional groups. We can't bond to it anymore. You name it. Or this can bond to the cross linkers, so these other molecules. It can bond to other oligomers. It can bond to other polymers that are much larger, other monomers. And so if you have a fully saturated resin, that is literally, if you just take your expensive SLA resin, you pour it in IPA to the point where it can't dissolve anymore,
Yeah,
right?
yeah.
Eventually, if you hit it with, with enough initiators, you will still see it will settle out. So because the polymers themselves are now no longer soluble. So it's all about that solvent, affinity, if you will.
Right.
Hopefully that makes a little bit of sense.
Yeah, no, that makes a lot of sense. And I guess that kind of explains how, for example, like leaving a saturated bottle of IPA out in the sun potentially does, like remove some of that
does
dissolve.
remove some of it. There will
Yeah.
still be components, like some pigments are, there might be polar pigments, non-polar pigments. They might actually dissolve into, the IPA. And no amount of exposure to the sun is going to remove that pigment.
Mhm.
And you can take, in some cases, a dyed, amount of IPA, and you can run it through a filter. You can get some of that pigment out,
Right.
but you can't get it all. Like
Right.
it still have a tint, and you can keep filtering and filtering and filtering, and all we're doing is statistically removing. Right. So we're just statistically removing an X number amount of those, those pigment molecules, or our photoinitiators, or oligomers, or plasticizers that are in there. So filtration can work depending on the size of the filter, the porosity of the filter, the amount of contact time, the pressure differential. There's all sorts of stuff that can go into it.
Right. But a lot of it is like statistical chance kind of, right?
Yes.
And like
correct.
even what you were describing earlier with like the free radicals, and even with using UV light to like try to catalyze these photoinitiators, like a lot of that is statistical chance, right?
Correct. It's all statistics based.
Right.
So we have to, as chemists, when we're designing these polymers, it's a lot of statistics. It's like, okay, well, what are the chances that we'll create an isomer? So an isomer is like a polymer, but it's mirrored in some way.
Right. Yeah.
So in cases like that, isomers can have different chemical properties because of how the electrons are formed, and so it's all statistics based. So
very interesting. Yeah.
Yeah.
So I guess my next question, which you kind of touched on already, is like these molecules are very, very small, right? And so you had mentioned, like if you run contaminate IPI through filters over and over and over, you might get some of the larger molecules like the pigment and the additives and stuff out, but some of the monomers, the oligomers, like what what are just so we have an idea of like
Yeah.
size? Like, yeah, what are the size ranges of these things?
So it really depends on the type of resin that you're using. Most of the time we're talking on the orders of nanometers, like
Mm,
single digit nanometers.
right. Wow.
Maybe even smaller, so fractional nanometers, depending on the molecule, of
Okay.
course. So these are really, really small. Like, scanning electron microscopes can't see these things.
Right. Yeah. And
you,
so,
you know,
yeah,
so
like the filters that most hobbyists are using probably are definitely not small
yeah.
enough for that.
Yeah, so you're not removing all of them. So if they are truly solvated in the solution, you will not remove them. It is physically impossible to get them all the way down, and removed. There will be some contaminant left over. Now, that being said, there are types of filters that may actually work,
Hmm.
and those can be reactive filters. So where there's an actual reaction that is going on. So, for instance, we have catalyzing filters for certain types of reagents, and we want to break down those contaminants so that we can filter them out. And so we'll have a catalyst that's usually covered on the surface of the filter. It could be a noble metal or a reactive metal. It could be a different molecule entirely. But what will happen is when those molecules touch each other, when they by chance happen to come close, it will then react, or it will split apart that molecule into two other molecules that then now have functional groups that we can bond to, or that have a specific affinity towards our filter, and we can bond to. So in many cases, what we'll see is like activated carbon filters. So carbon is great in that it's like the building block of everything.
Yeah, yeah.
And everything likes to bond to carbon. So, in many cases, what activated carbon is it's just a bunch of carbon that's got a really high surface area. And so we're increasing the probability that our molecules are going to bump in, and that they might be able to bond, or we might be able to, cause a reaction,
Right.
and it's going to stick.
And,
Um,
and
you know,
these are similar to how carbon filtration media like
mhm.
adsorbs VOCs out of like the
Yes,
atmosphere, right? Okay.
yes, yeah. So yeah, it could be on pore size. There's a bunch of different ways in which they can work.
Right.
It could just be on strictly on the pore size, so it traps the molecules of a certain size, because with activated carbon, we can make really, really small openings. Or, for instance, like molecular sieves. So we've seen molecular sieves used to be drying our solvents or whatever it might be,
Hmm.
because water can enter those, and there's an affinity for the water molecules to enter and get held there. But there's the pores are too large for other molecules to enter, and
Right.
so they just pass right over. And so this way we can selectively pull out what we're looking for.
Right. So it sounds like from a chemistry perspective, there are definitely ways that one could potentially use filters,
Mhm.
filtration, or certain
Yes.
media to kind of reclaim the IPA. From a practical perspective, how easy
Mhm.
is it to buy or find or make
Well,
something like that?
yeah, so I mean, I will say, like, some cases it makes sense to do filters. However, like, we have some apparatuses here that use filters, but filters will always have a cost
Right.
associated with them. At some point, they will stop working. They will become clogged. They will stop hitting their overall efficiency goals, and then we need to replace them. So there's a constant cost associated with that. So in general, it can be effective if you have a very specific need. Most of the time, though, filtration should be used for removing particulate. So,
Mm,
in the case where you have larger macromolecules, polymers of these SLA resin components, filtration isn't a bad idea. In that case, you can simply filter it off, and then now you have a solvent that is still mostly usable.
right.
It's not nearly as effective as a pure solvent, but it's at least usable in
Right.
that case. So yes, I am sure that you can build a filtration system at home DIY to filter your resin, and it would probably work to some degree.
Right. Yeah. Yeah. Well,
You know.
I think that one of my takeaways from like this discussion, and again, correct me if I'm wrong,
Hmm.
but one of my takeaways is that originally I had just been viewing it from a lens of like you have IPA and it dissolves certain components of the resin, and
Hmm.
once your IPA is saturated, then it just like nothing works anymore, right?
Yeah.
But my takeaway now is that there are actually two components. One is like the solubility in the IPA,
Hmm.
and then two is the statistical, like
Hmm.
mechanical cleaning or mechanical agitation part of
Yep.
it, right? And
Hmm.
it, I'm realizing now that, removing some of those bulk, larger particulates out from
Hmm.
the solvent or from the IPA can improve the statistical,
Yep.
mechanical cleaning part of the two things that I have
Yeah.
described. So,
Yep. Yeah,
yeah.
exactly. You got it. Yeah. So in general, yeah, as you continue cleaning your SLA prints, those larger macromolecules, if they're removed, you're going to increase your overall capability of continuing to clean with your solvent without having to fully regenerate.
Yeah, yeah,
Now, again, probably in the home game shop, many people aren't going to have a solvent still. They're not going to have the capability of regenerating. So, do I think that it's a valid option potentially to leave it out in the sun? Potentially, like, because what you're doing here is over time we're taking all of these molecules that are in solution and we're making for sure they're fully reacted. So we're exposing them to UV and then we're turning them into things that are no longer soluble and they will eventually settle out, or it's something that we can then filter off,
right.
you
Yeah,
know,
yeah,
because they're large enough that they can be, pulled out through a filter.
yeah. The
Now,
yeah,
it's not perfectly clean IPA. Let's get that straight. Like,
right,
there will still be components like the radical initiators. Once you break those down into their radicals, I'm using peroxide here. So, we have peroxide now, and then they'll form, and then there's nothing left. But in many cases, these SLA resins are using these really large molecules that are designed to produce a certain reactive component, radical component at a very specific time through a very specific energy. And there's always going to be a component kind of left over that just gets left alone.
right.
So, and that may be soluble in your IPA. And if it is, there's nothing you can do about it, probably.
Yeah,
It's just going
it's
to
just
hang
like
out there.
floating there forever.
Yeah. And it won't do anything. It
Yeah,
will just be there.
yeah,
Right. So the only way to get rid of that would be a distillation. Or, there are other ways in which you can get away with it. You can do, you could basically do solubility, so differential solubility. So, we can get a separatory funnel and we can pour our solvent in there. We can pour another solvent in that's not miscible with the first solvent.
right,
So, like with IPA, we know water's miscible. But sometimes like heptanes or other solvents, they're not as miscible. And so we can mix it, and then maybe the component that's in our solvent is more soluble in the secondary solvent. And so it extracts it,
right.
you know, and then, we can then dump that out. But then we have this complicated washing step where we're using a secondary solvent.
Yeah.
And then it's still in a solution with the solvent. So what do we do with
Right. So now
it?
you have to like try to separate that out too, right?
Exactly,
Yeah.
exactly. So
I
there are complicated ways of doing that,
yeah.
but
I guess that's because I've heard from, a few posts on Reddit that some people are also experimenting with like adding things in to try to precipitate out certain
sure.
parts of the resin. But it's the same problem, right? It's like it's this very complicated setup. Now you've introduced this additional
Hmm.
chemical into your solvent that do you leave it in there? Do you then have to remove it again? Like, yeah.
Sure. Yeah, and I mean there might be ways. So for instance, resins that potentially use like soybean oils or butyl esters or stuff like that, triglyceride based. Um, you know, in theory, you might be able to treat it essentially with lye, sodium hydroxide. And what would end up happening is those plasticizers would, undergo a chemical reaction. In which case, now they're no longer capable of staying in that solution of IPA. But that being said, you're now contaminating your IPA with with caustic lye, like,
Right. Yeah.
potassium hydroxide, sodium hydroxide, like, yeah, and like, arguably that's probably worse.
Right. Yeah. Yeah. It sounds worse.
I mean, again, it really depends on the type of the resin and the chemistry.
Yeah.
One thing that we actually get a lot of questions here at Gloop about is what can customers use to bond resin? And it's a complicated thing because resins have a variety of different chemistries. There's
Mm,
your Formlabs resins, you have a bunch of different offerings. Each chemistry is different. Each
right.
chemistry is unique. And in many cases, again, after we've cured the part, we are going for a fully cross-linked part, which means there's no functional groups left to bond to, or those sorts of things. I bring that up because depending on what materials you're washing in different resins, ideally, if you're doing this professionally, you have a dedicated washing bath for each particular
Right.
type of resin,
Right.
and you're not mixing those
Yeah.
because you don't know what kind of chemistry you're mixing.
Yeah.
Now, in practice, that's probably overkill.
Yeah. We we
you know,
we definitely do not do that just because
yeah,
I have like gosh, I have like more than 10 different Formlabs resins, right? Like a lot of the
yeah,
engineering stuff, and having
yeah.
to have an individual wash station for every one of those would just be a nightmare.
It probably would. Again, and that's why I say in practice, it probably doesn't matter. But,
Right.
if you're going from a purely analytical perspective, if you're wanting to keep your solvents as clean as possible and you're not cross-contaminating, or, ensuring that there's no contamination there, then yes, that's the proper way to do
Right.
things.
Yeah. 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 Yeah.
And I mean, in terms of like certain chemistries, like, they're some chemistries can actually have adverse reactions if you mix other types of chemistries, like, then now the whole thing doesn't work. you
Right.
know
Yeah. And I usually, again, kind of going off on a tangent here, but
Sure.
usually when I have to bond SLA parts, I will often use the actual resin itself as a
Hmm.
glue. But obviously there are challenges there, right? It's like if I have two parts with a very large cross-sectional area that I'm trying to bond, and let's say I'm using
Hmm.
a black opaque resin, I'm
Yeah,
not really going to be able to cure like the
you're
stuff
right.
inside, right?
Hmm.
So yeah.
Yeah. And so, I brought up the bonding thing mainly because of the different chemistries.
Right.
Because with every resin, the chemistries can vary. Now, as I said, most commonly the resins are going to be acrylate based. So in most cases, the chemistry isn't really going to matter that much. It's all roughly the same. It's just what plasticizer or what cross-linking agent they're using.
Mhm.
So, in some cases we can have a urethane, acrylate based cross-linker. So that we'll have a polyurethane oligomer with two functional groups of acrylate monomers on it, and then we can cross link up to two chains, or we can do even crazier different cross linkers. They can bond up to 4 or 6 or 8 different things all at once. And those cross linkers are the things that in some cases can be very temperamental.
Right. Yeah. Yeah. But I guess it does matter from a perspective of kind of what we were talking about earlier. Like if hobbyists are trying to use certain chemicals to precipitate out the
Hmm.
components from the IPA, or if they're trying to like filter for a specific size, or
Hmm.
using a filter with a specific affinity to certain molecules, then their mileage might vary between like a Formlabs resin versus like an Elegoo resin or something,
You're
right?
right.
Yeah.
Yeah, yeah, and I mean, because that chemistry is so different, the thing that someone says on Reddit, "Hey, you put this in there and it regenerates your IPA," it may not work at all.
Hmm. Yeah.
In fact, it might even be dangerous,
Right.
because you don't know what type of chemicals that you're mixing there.
Right. Right.
So,
Yeah. Wait, you mean stuff on Reddit isn't true? Isn't always true?
yeah, yeah,
This is actually super interesting. Like, I think, admittedly, before I chatted with you, I had a very, I don't know if entitled is the right word, but I had a very, like set opinion that the people
yeah,
who are doing this like have no idea what they're doing. It doesn't work. Like distillation
yeah,
is like the only method. But
yeah.
I think my mind is being opened a little bit more. Like obviously, as you've been saying, distillation is still kind of like the gold standard, right? It's like
Yeah.
complete separation, complete
In
regeneration.
industry, that's all we use. In
Right.
industry, if we need to regenerate our solvents, we use distillation.
Right.
Most always,
Yeah.
unless it's a very particular type of solvent or a very particular, product that we're searching for that might be temperature sensitive. But even then, we'll use vacuum distillation.
Right.
If it's temperature sensitive or unstable, there are different ways in which we can regenerate certain solvents. But most always, we're using a dedicated solvent still or some sort of rotovap sort of thing where
Right.
again it's distillation.
Yeah. Yeah.
So
Yeah.
yeah.
But yeah, again, your insights into like the statistical chance of like mechanical agitation and like
Hmm.
cleaning and filtering out solvent to try to improve that from
Yep.
chance of happening is really interesting, and it definitely was not on my radar. I didn't think that that mattered, but
Yeah.
it clearly must matter because so many people are doing it and claiming some type of efficacy,
Hmm.
right? So
Yeah. Yeah, and I believe that they will have some success, and it works. I mean, from the early days, I remember I backed the original Formlabs Kickstarter, so I got one of the
oh,
early,
number one, like
yeah,
wow,
I got
okay,
the Formlabs one, and I remember early on regenerating solvents, back in the day, just by literally blasting it with a bunch of UV light
right,
or taking it outside, setting it on the setting it on the ground and letting the light do the work. And
right,
I remember it working to some degree. Now I do also vividly remember the white Formlabs resin that came with that. It dyed the IPA, and it was not easy to get out. Yeah.
okay, yeah,
I mean, filtration worked a little bit, but I wasn't running this thing through a carbon filter or anything. I was
right.
just filtering it, and then um basically letting it reusing it.
Right, yeah, yeah. And it is actually pretty wild, like you were saying earlier, different formulations of resins matter a lot
Hmm.
because when I run the distillation machine on IPA that's washed, let's say, a lot of elastic or flexible resin, the junk
Uh-huh.
that's left over in the bag is like jello. Like I'm left with a very thick cake of jello. But then
Sure.
if I recycle IPA that's like washed a lot of glass particle filled resin, like what I
Uh-huh.
get is totally different, right? It's like a
Yep.
brittle cake of like glass particles, basically.
Yeah, yeah,
Yeah,
exactly. Well, and so that's another point is like if you're have a resin that has particulate suspended in it, like glass particles, like IPA won't solvate those. Like
right.
that will be something that can fall out. And so a lot of times as well, depending on the pigment load of the resin, users might be like, oh, hey, I'm filtering my resin, it's working. But what they're really doing is just removing the pigment.
Right, yeah,
That might be the only component, or it might be partial components of pre-polymerized or partially polymerized resin that they're
yeah,
removing, but
yeah.
still a lot of it is the unpolymerized stuff that's in there.
Right.
So
Yeah.
yeah.
I have definitely seen people who have statements of just being like, look, my IPA is crystal clear now. Like it used to be black because I'm printing black resin, but
Uh-huh.
yeah, it's probably like a lot of what you see there visually is like pigment, right?
Hmm. Yeah.
Yeah.
Yeah. And pigments will definitely throw off that perception because it's like, oh yeah, it's crystal clear. There's nothing left in it. And while that might be sort of true on the macro level, on the microscopic level, there's undoubtedly either photoinitiator in there or monomers or oligomers, dimers, trimers, you name it, that are
Right.
still in there.
Yeah.
Now again, given enough time inside of a UV light, or if you you can add a radicalizing agent into your resin that kickstarts that reactive chemistry, you might be able to remove a decent portion. But
Right. But
you
again,
know
that's up to like statistical chance and time
yeah.
and yeah.
Yeah,
Yeah.
and the larger and larger volume you have, like a molecule over here to get over there would take a very long time for Brownian motion. A
Right.
very long, if it ever is even possible, right?
Right, right, yeah.
Now that's again assuming that everything in there is perfectly still. Like some of the other things I know, like people are like, oh yeah, I'll leave this in the sun, and sun will create convective currents, and so that'll actually cause some agitation. It might even heat up the IPA, in which case we're increasing the reactivity because we're increasing the temperature. So these molecules are vibrating more. And
Right.
so they're more likely to bump into each other in the correct way and then polymerize.
Yeah.
So,
And I mentioned to you, like at the start of this call, I have seen some very elaborate setups where there's literally like some kind of pump. It goes through like a coil of tubing, clear tubing, that then is like blasted with these huge UV lights, and then it goes through like a three-stage filter. Like I mean, after this call, I am like more aware that that probably is doing something, but it's just it seems very elaborate and kind of
uh-huh.
intense.
Yeah. No, and that absolutely.
Okay, so I think like that answers a lot of how are we doing for time? 11, okay, yeah,
I
I
mean,
think we're
I'm
good.
okay if you need some more time.
Well, I booked this call for till 11:30, so I think we've got enough time.
Okay.
Yeah, I think we actually covered just covered a lot of the questions I had just organically, which is kind of fun.
Awesome.
The last two questions that I had was uh, number one is what is the easiest way to quantitatively measure whether you should change your IPA or like whether it's
Hmm.
saturated or not?
So that's a good question. And you know, generally speaking, you can use specific gravity, to kind of determine what concentration of solvent you have versus what's in there.
Hmm.
But the hard part is if you don't know what's in that resin and you don't know its solubility, you're not going to know exactly how far you can take it.
I see.
So the smallest, so you can add a small amount and you can get a drastic change in the specific gravity, or what appears to be a significant change. But in reality, it's still good. It's still good for cleaning.
Right.
So it might be difficult. Now, if you know specifically the resin that you're using and you can do some empirical analysis of saying, okay, when the specific gravity gets to this percentage, I am seeing I'm having to wash my parts a lot longer for that particular type of resin, then that's a good that you're able to correlate those things.
Right.
I don't know if it's possible to generalize a lot of this. It may be. This is something where I'll say that I haven't really done a whole lot of, like research in there or just experience that sort of stuff. I mean, I can say, speaking from experience, when we're looking at regenerating our solvents, we use specific gravity, but we also know what's in our solvents.
Right.
We
Yeah.
also know all of those components in there, and I can calculate the molarity. I can calculate exactly how much of that thing is in there to know when it's time to regenerate.
Right.
So in this case, there's a lot of unknowns because we
Yeah.
got our free radical initiators. We have our monomers, dimers, trimers, polymers, oligomers. Basically any additives, plasticizers. There's so many unknowns that it may be a little hard to quantify.
Right.
You know.
And I guess that also goes back to your point earlier where like, if you're not using an individual wash station for different types of resin, it's like you have no idea, right? Like all you
Mhm.
have is your relative baseline, which is like clear IPA
Yeah.
has X specific density, right?
Yep.
Yeah.
Exactly.
Yeah.
Yeah. Yeah.
Interesting.
So I mean, in general, again, how we calculate that specific density is we know the molecule size, we know its how its density in general, so we can calculate its specific gravity. But if we don't know the molecules that we're putting into it and they're soluble,
Hmm.
like yes, we can sort of calculate how much is in there. So yes, you can, but again, at the same time, we don't know their effects on overall solubility. We don't know how much of that particular element is soluble, or I'm sorry, molecule is soluble in our IPA.
Right.
You know,
Yeah.
so unless we had some data that says that we can only dissolve 3 kilograms per liter, or that's crazy. 3 kilograms, or 3 grams per liter or
Right.
something.
Yeah.
You know, like yeah, we can only do that. Then we know, okay, once we get to that specific gravity, now we need to regenerate. But the thing is, there's just too many unknowns there.
Sure. Yeah. Yeah. I guess that I guess if I were to do some testing, I had mentioned to you I kind of want to do some
Hmm.
experiments.
Yeah.
Although to be quite honest, I'm like leaning more towards just like posting this uh, call that we're having because I
Sure.
honestly find it so interesting, and I'm sure many other people would. But anyways, yeah, like I guess what I could do is basically just keep adding one type of resin into a
Hmm.
set volume until the specific density no longer changes or specific gravity no
Yep.
longer changes.
E-
And then, yeah,
Exactly.
yeah.
Yep. Yeah. So if you're noticing that you're adding and adding and adding to a point where it will come to an asymptotical sort of point where you keep adding and it's no longer dissolving. It's just going to end up at the bottom.
Yeah.
Now be careful. Just add in small amounts because what can happen is you can hit a point where then you cause one component to crash out. So
Oh,
yeah. So in chemistry you can get some
that's
crazy
so
interaction.
weird.
Yeah. So for instance, some components of that resin may be more soluble in the IPA than others. And so if it reaches a point, it can actually cause some of the other components to crash out because they're no longer soluble
Oh,
because of the solubility of the other thing. It has a preferential treatment,
so
right?
it'll,
So as we were talking, earlier, we could add things to our resin to cause things to precipitate. So we can change the solubility by sometimes we can add certain things, or in this case, just the natural addition of that resin can cause other components to no longer be soluble.
that's
So
so strange.
yeah, it is a possibility.
Right.
So
So if that happens at some point, I'll see like the specific gravity kind of plateau, but then change, like have like a step
You
change
might,
potentially.
but my assumption is you probably won't even that's such a small thing that you would probably overshoot it anyways and cause it to crash.
I see.
Like, and so you wouldn't be able to pick it up. You
Right.
would just look and say, oh yeah, this is what it is. But in reality, it's actually all of the stuff at the bottom. When you start seeing that, that's just like the plasticizer. It's
Right.
no longer soluble because you've the other thing is preferentially more soluble to the point where you've changed the solubility ability, equation for the other components.
Right, right.
So
Wow, okay.
yeah, yeah. No, I mean
Very,
again,
very interesting.
that's a small edge case. Again, what's in theoretically possible and what's realistically practical are two different worlds.
Sure. Yeah, yeah. That's very interesting though. Like, yeah, I'm so green to all this like chemistry stuff.
Yeah.
Wow. Yeah, okay. So my last
Yeah.
question is so we've talked about how doing some of these things does um help one use solvent like potentially
Hmm.
longer, but that distillation is still kind of the best way to fully separate and
Hmm.
reclaim the IPA.
Yeah.
Is there, are there any other ways in which people could try and have a full separation um,
Hmm.
without, you know, needing a chemistry lab or without needing to have very special equipment?
Yeah.
Like one thing that's kind of on my mind is I know that the saturation point of solvents changes with temperature, right?
Hmm.
So
You got it.
I believe when it's warmer, or I believe the higher the temperature, the more it can.
Typically, the more soluble things can become.
Yeah,
But that depends on the molecule itself,
I
because some
see.
molecules can become unstable. But generally speaking, the higher the temperature, the more soluble something can be.
Right,
So, and the colder it is, the less soluble. So, if you're asking, can someone chuck their IPA in a freezer? Potentially,
right.
and change the solubility. So, you cause certain things to crash out, and then, yeah. Um, eh, that's differential solubility through temperature. As we mentioned before, you can try and take, immiscible solvents and mix them that have, a higher, the component has a higher solubility in, and it's able to pull it out. But now you're left over with, another solvent that, is stuck with stuff. You could try the UV exposure, letting it fully cross-link, polymerize, and then filtration,
Mhm.
or just the overall letting Brownian motion take course and see where the stratification can happen, and then decanting.
Right.
That is also possibly a solution.
Right.
But if you're going for probably the best, it's still going to be distillation.
Okay.
Now in distillation, I mean, with IPA, there's also this other thing where exposure to air will cause it to incorporate water moisture.
Yes.
And there is no way around that. IPA in the 70-ish% or higher, it's still hygroscopic, so it's going to pull water out of the air. And if you want 99%, like you're going to have to constantly be adding molecular sieves
Right.
to that resin in order to keep that at that rate. And distillation will not change that, because we will form what's called an azeotrope. So an azeotrope is this really cool thing where the boiling point of two solvents that are miscible is lower than the boiling point of the individual solvents themselves. So the most common
Oh.
azeotrope is ethanol and water, or in many cases alcohol and water in general. So you're not able to get it any higher than about give or take 90% for like ethanol and water, because a 10% ethanol 90% water mixture, I'm sorry, other way around, 90% ethanol 10% water will boil lower than the 100% ethanol. So when you're distilling it, you have a 10%, 90% mixture of ethanol and water, and it will then come over and it will boil at a lower temperature. So there's
Mm,
literally no way to remove that water through distillation,
right.
because it forms this thing called an azeotrope. It, its boiling point is reduced with the addition of water than the individual solvent being pure. So the
Right.
only way to remove that is through a molecular sieve in that case.
Right.
So,
I've
or a
always,
drying process.
yeah, that's a really uh really good point, because I've always wondered that, right? Like
Mm-hmm.
so I've known that IPA is very hygroscopic, and I've always
Yep.
wondered, like, okay, the boiling point that the distiller is set to for IPA is, I believe, slightly higher, or like
It,
around the boiling point of water.
yeah.
Yeah, and
Yeah.
so I've always wondered if I'm just also boiling the water and it's just going back into the
Yeah, well,
container. So
you will always be boiling the water because it's
yeah,
forming an azeotrope. I can't remember off the top of my head, but I believe that azeotrope is somewhere around the 80% or so.
okay,
I could be wrong. I'm just trying to remember off the top of my head.
yeah,
But yeah, so basically the highest that you will ever get purity back over time,
right,
if you're constantly going through and you're just exposing it to air, would be somewhere around the 70 to 80% range, I believe.
right, okay, okay,
So
huh,
yeah, it's impossible to remove the water through distillation.
right,
Now you could do fractional distillation under vacuum. That will change so pressure changes the boiling temperatures, and so that can drive it further, so you can get a more pure solvent. But you will still have that issue of the azeotrope. So
right,
the azeotrope being that the combination of the water and alcohol will boil lower than just the alcohol or the water alone.
right, right. Yeah,
So yeah,
that's super interesting,
yeah,
because
it's
that,
really
yeah,
weird. So if you're looking at the graph, like of percentages, 100% alcohol will actually have a higher boiling point than 90-10. There's like this weird little dip.
right, huh,
So yeah, you'll be able to distill up to a certain point, and then it'll dip,
right,
and that's because the weird interactions of these molecules. So when we're adding energy and we're basically turning it to we're increasing the latent heat of vaporization. So it's now converting from a liquid to a gas, and it's vaporizing. It will pull that water with it because
right,
they're complex interactions,
yeah, yeah,
and it just goes with it.
yeah,
So yeah.
huh. And I guess if one were to try and use molecular sieve, like, do you just literally throw it into the solution?
Throw it in.
Oh,
Yeah, just
okay.
throw it in.
Okay.
Yeah. So the best way to do it would be is if you wanted to try and regenerate your solvent to have a higher overall concentration compared to the water, you'll take after your solvent still inside your bucket there, you'll just dump in a decent amount of molecular sieves. Now, I will say that because you're removing the water, that is going to be an exothermic reaction. So you will increase the temperature of your, because thermodynamics here, you're going to increase the temperature of your alcohol. So be
Right.
careful, because if you just take all of the molecular sieves and dump it into your solvent, you may actually cause that solvent to boil, because if there's enough water in there and it gets sucked in, right, you're adding order to a system that
Right.
that has
Yeah.
entropy,
Yeah.
and so you're removing and lowering the entropy, and that takes energy.
Right.
And that energy is in the form of pure dry molecular sieves, and that energy is released in the form of heat.
Right. Okay. I will keep that in mind. Yeah. And then
So
probably also you don't want to like close the vessel and create a pressure vessel.
no,
Yeah.
yes, I'm speaking from experience here. In my early days, I may have taken a vessel, dumped a bunch of molecular sieves in, closed the thing, and had a very fun, very fun explosion.
Okay, that is very good for me to know. I don't know if I will ever attempt using molecular sieve, but I mean it sounds like it's not too difficult, right? Like you
No,
pour it
it's
in and then
pretty
you just have
easy.
to take it out and regenerate the sieve
Yeah,
on
yeah.
its
So
own.
3A or 4A molecular sieves, kind of your choice. They both kind of work similarly.
Right.
And you just make sure you get high quality ones, and then you'll throw them in, and then uh, you probably want to mix and that sort of stuff. But molecular sieves, what they'll do is they'll create a gradient. So again, here's some other fun chemistry stuff. We have our molecular sieve. Imagine it being a point, and we have our water molecules that are dispersed throughout our solution, and eventually they'll want to come in, and they'll be like, oh hey, I can go in here, so it'll go in, and now the solution around it is of lower concentration, or higher concentration of the solvent compared to the water,
Right.
and so we are now creating a gradient. So what we'll have is it'll be a pumping action.
Mm,
So it's called a diffusion gradient. So the water molecules will want to go towards the pressure. It's a pressure difference essentially, and they'll naturally gravitate towards this gradient, and they'll naturally find their way in. So you don't have to mix it, but mixing it accelerates that reaction.
sure. Yeah, yeah, yeah. Okay.
So
Yeah.
yeah, that's also another fun thing when we talk about the hygroscopic nature of filaments or other things like that, like how actually the water molecules will bond onto the surface and then eventually work their way into the core of the filament, all sorts of fun stuff.
Right,
And
right.
why just putting your filament inside a bag with desiccant doesn't necessarily dry it.
Right. Yeah. Very interesting. Okay. Yeah, I
Yep.
might have to get some molecular sieve. So
Yeah.
you're saying like in general, the concentration kind of ends up at like 75 to 80%,
I believe
somewhere
for
around there.
IPA, I believe for IPA, I could check for you, but off the top of my head, I believe it's somewhere around there. I know like
Right.
ethanol, I know ethanol is somewhere in the 90th percentile.
Hmm.
So I think IPA is a little bit more hygroscopic than ethanol, if
Okay.
I remember correctly. Um, and
And
so it would end up around the 70-ish percent, 65, 70%, something like
okay,
that.
okay. That's
So
actually
maybe,
quite a lot.
yeah, it can hold quite a lot.
Yeah.
Now, I'm not saying that it would get to that just by just leaving it out in the open over the course of a couple hours, even days. I mean, that's a lot of water. If you have a liter of IPA, and let's say it gets down to even the 80%, that's 200 milliliters of water essentially that you're going to have to pull out of the air.
Right, yeah.
So like it's not going to get to that in that short of a time frame.
Yeah, yeah.
You know,
Unless you're like in the rainforest or something.
yeah. So,
Yeah.
I mean, it would, it would take a little bit, but over time, it would eventually get there. So, one of the fun experiments that I did a while ago, this was with Pooch, was different saturated salt solutions, and then taking them and putting them in. So, saturated salts, we could take like lithium chloride or calcium carbonate or various different salts, and we can mix them with water to where we create a slurry. So it's
Mm,
a slurry of salt and water, and then we can take and put it into a 100% humidity environment. So it's a closed chamber where we're increasing humidity crazy. These saturated salt solutions would want to achieve a certain dedicated humidity. So like lithium chloride is 10% relative humidity. So it would keep pulling the water out of the air until it reaches a certain humidity. And so
right.
what you can see is that actually the water would increase over time as it mixed with the salt.
Oh,
And so we could see the amount of water that you're able to pull out just by
that's pretty
using
cool.
salt. It was a
Yeah.
really fun experiment. So it would be the same thing. Like if you had your alcohol and you just put it in there and you had an environment, so you have a graduated cylinder. Yes, some of the alcohol would evaporate into the atmosphere, but is provided that there's always a constant partial pressure and the alcohol isn't evaporating and condensing down, you would see the alcohol eventually increase in volume as
Right.
it pulls the water in.
Huh.
So
Wow.
yeah,
Okay. Yeah.
yeah.
So I had purchased some hydrometers, and I think I bought two. One of them just measures specific gravity within a certain range, and
Hmm.
then the other one, I'm not exactly sure how that works, but the other one I think tells you the concentration of IPA specifically.
Yeah,
So I'm super interested to take some of the IPA that like
yeah.
I've like recycled over and over.
Uh-huh.
Obviously, I lose some through evaporation, and I have to reintroduce
Yep.
new 99% IPA
Hmm.
over time. But I'd be curious to put that hydrometer in there and see what percentage concentration I'm actually getting.
Yeah, I'd be curious to know what you're at too. I mean, my
Yeah,
guess is you're probably going to be somewhere close to the high 90s.
right.
I would just assume here. It it just really kind of depends
Yeah,
exactly how humid your environment is, how many times you've recycled it, all of those things.
yeah,
And I mean, most of the time you're probably having it in a relatively enclosed container. Maybe it's not
yes,
perfectly enclosed, but you know,
yeah.
yeah,
It's usually enclosed, and also, as I said earlier, I am kind of every recycle like cycle, I'm always adding a bit more fresh
yeah,
99% IPA. So it's hard to know where I'm at, but I'll definitely let you know when I get to
yeah.
that. Yeah.
Yeah. So those hygrometers, those are tuned for that show the percentage. Are basically just they're almost identical to the other one that just measures the specific gravity instead of the specific gravity scale. In a human readable format, it's just a percent based.
Oh, I
And
see.
they calculate it based off of again they'll take their IPA and they'll mix it with a certain concentration of water.
Right.
So now as we were kind of talking about earlier, if you mix it with resin and you put that one with the concentration in there, it might say something wild like it's
Right.
10% concentration or something,
Yeah, yeah. Because it
because
assumes
yeah,
alcohol and
yeah, it
water.
assumes that's alcohol and water, but
Right.
it's not. Like, or it might just not really make a difference, because again, it's still mostly alcohol.
Right. Yeah, yeah, yeah.
Yeah, yeah,
Huh. Yeah, well, I think that was all the questions that I had regarding like recycling of IPA.
awesome.
This and like thank you so much, Andrew. This has been
Yeah,
really fun and actually really educational for me.
yeah.
So I really appreciate your time.
Yeah, no, thank you for reaching out and setting us up. I mean, hopefully, it helps understand, and I'd be happy to do more of these if you want. So
Sure. Yeah. Yeah. And I really am leaning towards just posting this chat online because I think it would be very educational and interesting for many people who
sure,
kind of want to dive into the deepness of this as
yeah,
I have wanted to. So yeah,
yeah.
yeah.
Yeah, no, and I'm definitely curious of your experiments that you'll run. Hopefully, when you get some time.
Yeah, I definitely do want to run them. Just yeah, right now it's like so busy. Sorry, I'm just
Yeah.
gonna stop recording, and then
Oh,
we can
you're
just
good.
keep
You're
chatting.